The set of reciprocal lattice vectors G determine the possible X-ray reflection Consider a beam of X-ray is incident on a crystal Consider a small volume element dV in the crystal. At a distance or from the origin. This is the crystal specimen. We are considering a small volume del V inside the crystal, and the incident ray is interacting with the small volume del V. This is the origin, distance R. Incident and reflected beam. The incident beam direction is wave vector k, which is in the momentum direction, E is equal to h cut k. Similarly, k prime is the reflected wave. The incident wave has a wave function psi incident, which is E iota k dot r, while the reflected wave, the wave function E iota k dot r. The path difference of the incident beam k vector at r with respect to the origin O is r sine pi. Let us draw a perpendicular from this origin O on this incident beam. This is angle pi. This is angle 90 degree. So the angle between the volume element and the origin, this is theta. This angle is phi, and this is 90 degree. So this part difference is equal to r sine phi. The corresponding phase difference is equal to 2 pi by lambda into the path difference, which is equal to 2 pi by lambda r sine phi. This is 2 pi by lambda r cos 90 minus theta. 90 minus theta is r sine phi. So the phase difference for the incident wave is k dot r. Similarly, the phase difference for the reflected beam with respect to the origin O is minus k dot r. The total phase difference is equal to the sum of incident and reflected phase differences. Thus the total phase differences is equal to k dot r plus k prime dot r, which is k minus k prime dot r. The corresponding phase factor is e iota k minus k prime dot r. The amplitude of the scattered wave from volume element dV is proportional to local electron density. Nr, that is, the scatter wave amplitude is represented by F is equal to integral over the Nr multiplied by the phase factor of the incident and reflected wave over the whole volume dV. This gives us the scatter wave amplitude which is equal to the electron number density multiplied by the phase factor of the two waves, incident and reflected beam. The scattering vector del k is k prime minus k. K minus k prime is minus del k. Thus, F is equal to integral nr e minus iota del k dot r dV. Similarly, the number density nr is equal to summation over g n g e iota g dot r. Putting the value nr, and this is equation 1. In n1 we get the scattering factor as integral over the volume dv ng e iota g dot r and e minus iota del k dot r. This is equation 2. So f is equal to integral dv ng minus iota g minus del k dot r is equation 3. Equation 3 gives us that the scattering amplitude f will be maximum when g is equal to del k, that is f is equal to integral dv ng e iota g minus del k dot r. At g is equal to del k, f gives us this term goes to 1 ng dv, the integral means v ng. This means the scattering amplitude will be maximum when g is equal to del k. This means there will be a diffraction with a bright spot. If g is not equal to del k, then there will be no diffraction. G is equal to del k is the diffraction condition. This equation shows that the difference of the two vectors k and minus k prime or k and k prime must be equal to g, where g is a reciprocal lattice point or the distance between two points in reciprocal space, which is called reciprocal lattice vector. This means if these are the reciprocal lattice points and this is our reference and this is point 1, so this is vector g, which is the reciprocal lattice vector. If the sum of the incident and the diffracted beam is a valid reciprocal lattice vector, then the diffraction holds, and if the difference of the two vectors k and k prime is not a valid reciprocal lattice vector, then there will be no diffraction. As we have considered The interaction is elastic, where k is equal to k prime. Thus, del k is equal to g, or k prime minus k is equal to g. That is, k prime is equal to k plus g. Let us check simple mathematical tool, which is k prime square is equal to k square plus 2kg plus g square, or this gives us 2kg plus g square equal to 0, that is k prime is equal to k. Here the diffraction condition holds when if these are the set of parallel planes. This is the incident beam k prime, direction of k. These are parallel planes. This is del k. Angle theta, this is 90. So 2k dot g plus g square equal to 0 f 2k minus g, and plus g square means minus g's. So g square is equal to plus 2k plus g square equal to 0, and we have 2kg is equal to g square. The equation 2k dot g is equal to g square. For every g there will be a g in the opposite direction. So 2kg cos 90 minus theta from the figure is equal to g square. That is incident k prime, direction of k, del k, theta 90, and this is 90 minus theta. So 2kg sine theta is equal to or 2k sine theta equal to g. Here g is 2 pi by length dhkl, a reciprocal lattice vector, or dhkl is 2 pi by g. So k is 2 pi by lambda, sine theta is equal to g. G is 2 pi divided by d HKL. So 2 d HKL sine theta is equal to lambda. So which is the Bragg's law. Here theta is the angle between the plane and incident wave. To summarize our discussion, the diffraction condition in the real lattice is 2d sine theta n lambda. This is a real lattice, also called scalar form of the Bragg's law, and the diffraction condition in the reciprocal space is del k is equal to g, or 2kg is equal to g square. This is in reciprocal space. So vector form of the Bragg's law, and we use k space and use Fourier series for the analysis.